The next topic is on electrostatic potential, potential surface, and their relations to the electric field. So potential, what do you know about potential? I mean, in circuits, I'm sure you come across the word potential difference. Okay, so what's potential difference? Voltage, yeah. So the voltage is a difference in potential. So similar here. Okay, so the learning outcome that we expect you to acquire at the end of these topics, to be understand the meaning of potential and voltage and be able to relate that to the electric field. And also understand the concept of equipotential surface and to sketch this for simple charge distributions. Find the potential difference from the electric field and vice versa. Okay, so the potential difference that you talk about in circuit is also directly related to the electric field. And here we want to look at how you can determine the potential difference from the electric field. So if you know the electric field, how you can work out the potential difference. Okay, electrostatic work. So if an object is moved a distance x against a force F, the work done by the force on the object is F times x, a scalar quantity measured in joules. And we can define a vector x known as displacement vector so that the magnitude of x tells us the distance moved by the object. The direction of x tells us the direction of the movement. The general result is that the work done W by the force on the object is W equals to minus F dot X. Okay, so this is dot products of two vectors. So we know that force is a vector and that X is the displacement. Okay, how much you move the object in a particular direction. And then the minus sign, this is due to the fact that the force only does a positive amount of work on the object if the objects try to move in the opposite direction of the force. So if F is not parallel to X, only the components F along the X does the work, hence scalar products. Okay, so depending on, so if I have an object, this is the force. If I move this direction, that is perpendicular to the force, therefore there's no work done in this scenario. If I move it in this direction, only these components of the displacement that actually has work being done to it. Okay, not in this component because it's a dot product of the two vectors. Okay, so the force is a vector, the displacement is another vector, so only the components in the force direction that actually produce work. So if a displacement perpendicular to the force results to no work, since F dot X will be equal to 0. So in this scenario here. So that is, if you're talking about moving an object in a direction of the force, that's all mechanics. Okay, so here we want to look at electrostatics. Suppose we now take an object with a charge Q and move it within an electric field. So we have an electric field, we have a charge. If we want to move the charge in that electric field or in the direction of that electric field, and want to work out what is the work done by the field. Okay, so the work done by the field, so if we move it by a small increment of dl, then it will be minus F dot dl, and we know that F is equals to Q times the electric field. That will be E dot dl, and that is the work done by the field during the increment of the displacement. Okay, example here. So the displacement is dl. So if I want to move my charge from A to B, if I move along this, then I have to work out the force or the electric field in this region dot with the displacement, and then sum it all up all along this path. Okay, so there will be the integral of E dot dl, and I work out what is the work done moving the charge from A to B, okay, along this path. So equation 1 define the electrostatic work done. So electrostatic work done dW is equals to minus Q integral of E dot dl. So the total work done needs to add up all the increments amount of work along the path, perform a path integral. This is my path integral, E dot dl. Okay, so summing up along all this dl along this path. So is the work done by the electrostatic field E in moving a charge Q between 2 points within the field. So it will be easier. So just now we move along a path, okay, a curved path here. But if we know the electric field, okay, so if I have my electric field pointing from A to B, it will be easier to compute if I choose the path which is along the electric field. Okay, so if my path is in the same direction of the electric field, then it will make this integral a lot simpler. Okay, so E dot dl becomes just a scalar, which is E times L. Okay, so very important point. So we do mean E in equation 1, not the electric flux density. Is this the electric field that we're talking about here? So we're dealing with the electric field with the field inside a dielectrics, which takes the usual rules of finding D first, then find E, and then it is the electric field that we want in here to calculate the work done. Okay, but if we want to find electric field, earlier on we talked very often that if we want to find electric field, we'll go through finding the electric flux density. But in here, we are treating it the electric field rather than the electric flux density. It is the electric field that actually do the work. So it makes life easier if we try to move along the electric field line. Okay, so if we choose the path of the displacement along the electric field lines, then the integral become a lot simpler. Okay, so rather than going this way like we did just now, and this become very difficult integral because we have our electric field in here, and then we need to solve this dot products, and here we need to find out the electric field here, and then need to do this dot product, and then we need to sum up all the path to find the total work done. So it will be easier just choose the path where the electric field is, and then the displacement will be the electric field or integral E dl. And if the electric field is constant, this is simply equals to minus Q E integral of dl, and dl is simply just the path length. Okay, so an example. A +1 microcoulomb charge is moved a distance of 0.3 millimeter in the direction of a uniform electric field of magnitude . Okay. Example. A 1 microcoulomb charge is moved a distance of 0.3 millimeters in the directions of a uniform electric field of magnitude 150 watts per meter. How much work is done by or on the charge by the field? Okay, so we have a charge 1 microcoulombs, move a distance of 0.3 millimeters in the directions of, we have an electric field, uniform electric field E, and then we have a charge here. We want to work out how much work is done by the field on the charge to move it of a displacement of 0.3 millimeter. Okay, so maybe spend 2 minutes, try to understand what the question is talking about. If you can solve it, that's great, go ahead and solve it.
Is that milli or microcoulombs?
It's millicoulombs, I think.
Okay.
Yeah. Okay, so the equation is minus Q E dot dl. So what is the work done in joules? So uniform electric field. Okay, so we move the charge along the electric field lines, so we can use equations 2. So instead of using W equals to minus Q integral vector E dot the displacement dl, and because we go along the electric field, so this dot product is simply equals to the magnitude of the two multiplication, so we don't have to resolve. So what it means is that this is my E field. We are also moving dl in the same direction, so E dot dl is simply equals to E times L. So if we are not moving along the field, if we try to move this in this direction, then E dot dl is not equals to E dl. This equals to E dl. You need to know this angle here, cos theta. Okay, and that becomes more complicated. Okay, so because we are in this scenario, so we can make the work done W equals to minus Q integral D dl, and because E is uniform, so therefore it's constant along the whole path that you're moving. Because constant, you can take it out from the integral, and therefore that integral dl is simply equals to the displacement that you have of that charge, which is L. And therefore this is equals to minus 0.001, which is the charge, times 150, which is the electric field, and then times the displacement, which is 0.3 millimeter, and that works out to be minus 4.5 times 10 to the minus 5 joules. So negative work here means that the positive charge want to move in the direction of the field. So we have the electric field. So it's a positive charge. So negative work done means that if you put the charge there, the charge will move along the electric field. So the field actually gain energy rather than losing energy by working on the charge. If the charge was negative, then the field will have to do a positive amount of work, since the movement opposed to the direction of the field. Okay, so the field needs to work harder to move the charge. Potential difference, V, we just talked about that, and voltage. So suppose an electric field does an amount of work W in moving a charge Q between 2 points in electrostatic field E. We define the potential difference V between the 2 points, or equivalent to the voltage between 2 points, as the ratio of V, or ratio of the work done W to Q. Okay, so just now we said that V is equals to minus Q E dot dl. And now we define that the potential difference V is equals to V divided by Q, and that will be equals to minus. Okay, so a potential difference is equals to minus integral of E dot dl. And earlier on we said that our electric field, units of electric field, is watts per meter. Okay, so our V has a unit of watts. So our electric field dot dl, dl has the units of meter, and therefore this gives you our potential difference is equals to the integral, minus integral of d dot dl. Okay, so this is general expression for potential difference, which is minus the integral of E dot dl. Again, if we define the path to be along the electric field, then it's simply equals to minus E dl. So we often refer voltage across the terminals of a power supply. This is the same as the potential difference across the terminal. Okay, so we said that we use a 12 watt supply, for example. Okay, so that is the potential difference between the plus and a negative terminal of the supply, which is the potential difference. I'm sure you know that. So, definition of potential difference between 2 points in electrostatic field is the work done in moving a charge of 1 coulomb between 2 points. Okay, although it said it's not very rigorous because again 1 coulomb charge is rather big, but that's the idea. Okay, so which means that if Q is equals to 1 coulomb, then my work done is equals to V. Okay, so basically moving this 1 coulomb charge between 2 points will be the potential difference. Okay, this is an example here. Maybe you can take it away with you and have a look, and then we'll discuss this in the next lecture.